Hey, this is Owen Priest for Science in Society. So, quite a while back, I did a blog entry for Science in Society where I told you about Professor Rick Van Dyne in the chemistry department here at Northwestern University and work that he did on a technique he developed known as surface-enhanced Raman spectroscopy. Now, if you didn't get a chance to watch the previous blog entry, then what you can do is click here, and then once you've watched the previous blog entry, you can come back and watch this. Okay, so when I interviewed Professor Van Dyne about his research, there was a paper that had not yet been published, and so I didn't talk about the paper, and there was an image that he showed me in his office that because it hadn't been published yet, I wasn't able to show you. Well, that paper has been published now, and I'm able to show you the image. Now, when I talked with Professor Van Dyne about his research and about this image, what he said was,
we have a paper that's actually under review right now, which is addressing a famous Winslow Homer watercolor painting.
Which one?
It's called Farmer's Boy. And in that painting, in that watercolor, the sky, which was recorded in Winslow Homer's diary as a vivid evening sky, is completely washed out and looks like a cold gray day in Chicago. The hypothesis was that photochemistry, light shining on the painting, had destroyed the color, and that didn't represent the original color. So we went back with a microscope version of the surface-enhanced Raman scattering to be able to look at very tiny grains of pigment and found the original colors of the artwork. And we've also created a digital reconstruction of the image that we think represents what the pristine image is.
so here's the image he is talking about, with the washed out sky on the right. That's what it looks like today. On the left is the digital reconstruction where you can see what it looked like when Homer painted it. Pretty cool, huh? Now, at the end of my interview with Professor Van Dyne, he told me that his technique opens up
a whole new area of almost forensic investigation, if you will, of artworks. Think of CSI for art, and we will be able to reconstruct what damaged paintings look like, and therefore have a scientific basis for restoration of the paintings and authentication of great many things.
And when he said that, it reminded me of when I was in high school and the ceiling of the Sistine Chapel was being restored, and there was a lot of controversy around that restoration. In the past 400 years, there have been a couple of restorations to the ceiling of the Sistine Chapel. One of the goals of this particular restoration, which was started in 1980, was to remove hundreds and hundreds of years of accumulated grime from candle smoke, mostly comprising wax and soot. Now, if you look here at a picture of the chapel ceiling before the restoration, you can see that everything looks, well, very dull and dark. In an image of the restored ceiling, you can see that everything looks quite a bit brighter and the colors are much more intense. Now, while some say that the restored ceiling looks fantastic, there are critics who say that during the restoration process, some of Michelangelo's original work was stripped away. Part of the controversy surrounding the restoration revolves around whether or not Michelangelo only painted on fresh, wet plaster, or after the plaster dried, did he go back and add anything or touch it up at all? And if he did do any additional work, well, just how much did he do? These are important questions to be answered in the world of art conservation and restoration. And this is where science can lend a hand. And this is why I think the work of Professor Van Dyne and his collaborators at the Art Institute of Chicago can be really cool. Now, I'm a chemist, not an artist or an art critic. But I do see the point of some critics when you look closely at some of the restoration work. For instance, if you look at these before and after images from the Sistine Chapel restoration, there's a huge difference in the coloring and detail. An important question is, what were the materials that Michelangelo used, and did he intend for the colors to be so bright? Or did he go back and do something to the frescoes after they had dried? Was the material removed during restoration all from candle soot, or was some of it part of the original work? Look at how obvious this is in these two images. You can see that there is fine detail, especially in the architectural relief above the figure, that has been lost during the restoration. And look at the eyes. In the unrestored fresco, you can see the eyes of the figure. In the restored image, the eyes are gone. The eyes were stripped away during the process of stripping away the carbon black, the grease, and grime from accumulated candle soot. So the question is, did Michelangelo himself paint the eyes and the detail in the architectural relief above the figure? Or was that done at a later date, maybe during one of the previous restorations? Did Michelangelo intend for the colors to be as bright as they are now? Or did he intend for things to be more muted? What is the chemical composition of the material removed during restoration? And was anything removed that was part of the original fresco? What is the exact chemical composition of the material used in the detailing of the frescoes? If it could have been determined what the exact chemical composition was of the material that was used in the detailing of the architectural relief or the eyes of the figure, well, if that material was known to be in Michelangelo's palette, then it could be determined maybe that that was his original intent, that was his original work. Or if surface-enhanced Raman spectroscopy could be used to rule out the fact that, no, that was not part of Michelangelo's original work, well, then maybe a lot of the controversy surrounding that restoration could have been avoided. So when I think about this, I think about how, wow, isn't it really neat how we can use our science to better understand the world around us. In this case, to understand the world of art better. And I'm reminded about how cool chemistry can really be. Food for thought. That's all for now. And so until next time, this is Owen Priest for Science and Society.